Welcome back to differential equations. This is part 2 of our lecture on exact equations. In part 1, we introduced partial derivatives as we're going to use them and related total differentials to ODEs. In this part, we're going to get to what an exact equation is and then how we solve them. All right, we're going to go back to our intro example. In the first part, we took the differential equation and rewrote it in what we're calling differential form. Basically, we try to separate it, and we put the x and y differentials all on the same side. All right, the reason for doing that, before moving on, is that the ODE in differential form looks very similar to what we went through in part 1 on total differentials. All right, so let's define this, what we're going to call an ODE in differential form. We'll define it as being a differential equation in this form, m dx plus n dy equals 0. And we're going to interpret m and n both as being functions of x and y. All right, if we go back to our intro example above, we can identify m, what's multiplying dx, as 2x plus y squared, and we can identify n, which is what's multiplying dy, as 2xy. All right, now with the idea of an ODE in differential form and total differentials under our belt, we can understand the definition of what we're going to call an exact equation. All right, and it has a lot of terms built into it and ideas, but the definition is, we'll say an ODE of this form, m dx plus n dy equals 0. This is called an exact equation if that left-hand side, m dx plus n dy, is the total differential of some function of two variables. That's a mouthful. What does that mean? Well, if we have a function of two variables, which we call the potential function, that'll make sense when we relate this to a Calc 3 topic in a little bit. What we want to be able to do is take this function of two variables and then calculate the total differential of that to get this differential m dx plus n dy. All right, now if we start with the function of x and y at the top there, and we actually calculate the total differential, remember we calculate the x and y partial derivatives of the function, multiply by dx and dy, and then add them together. And what we get here, taking our ODE in differential form, m dx plus n dy equals 0, of course, we're going to identify that that looks very similar to the total differential we just calculated. We're forced into having that the x partial derivative of the function has to equal m, and the y partial derivative of that function has to equal n. Those equations or conditions at the bottom, they're going to play a role in what we get to immediately after this. All right, so with these terms and definitions out of the way, let's go back to those two questions that we posed in the first part of the lecture. The first question is basically, when is an ODE exact? And what we mean by that is, when is an ODE the total differential of some function of two variables? All right, so in order for us to be able to solve one of these ODEs in differential form, we're going to have to determine if it is exact. In other words, if there is a function of two variables that results in that total differential. All right, once we have that criteria, if the equation ODE, if it is exact, then how do we solve it? And that amounts to us finding that function, what we've been calling f of x comma y, what we call in mathematics and physics the potential function. So if it is exact, how do we find that function? How do we find the potential function which solves the ODE? All right, so let's answer question 1 first. There is a simple criteria for an ODE in differential form being exact. All right, and if again we start with our basic form, m dx plus n dy equals 0, the condition for this ODE to be exact is that the y partial derivative of m has to equal the x partial derivative of n. Now, in red down here, for those of you that have completed multivariable calculus, a very brief explanation for why this condition exists, where it comes from. It's due to the equality of the mixed second order partial derivatives. In Calc 3, that's known as Chloro's theorem. So due to Chloro's theorem, the equality of those mixed second order partial derivatives, we get this condition for exactness. All right, don't worry about that. If you haven't taken Calc 3, this will make more sense if and when you get to that course. All right, let's go back to our intro example. So we're going to write it in differential form. Earlier in this part of the lecture, we identified m and n. M is 2x plus y squared, and n is 2xy. Is this ODE exact? Let's apply our criteria above in the box there. So with the function m, we differentiate it with respect to y, and we get 2y. We take the function n and differentiate it with respect to x, and we also get 2y. And our criteria then says because those partial derivatives are equal, our ODE is exact. What that means is the function of two variables, what we've been calling f of x comma y, that function exists. So now that we know that function exists, because this ODE is exact, we can go forth and then try to find it. If the ODE is not exact, we can't find this function, as we're going to learn momentarily. All right, so this right now is our criteria for exactness. Something about the partial derivatives of m and n with respect to kind of the opposite variable being equal. All right, the second question, how do we find this function? This is addressed at the bottom here. And our goal is to go from the given ODE, so we're going to know what m and n are in the given problem. What we're trying to figure out is what is the function f. Now, previously, we had this condition for what the partial derivatives of f with respect to x and y should equal. They should be m and n respectively. So what we have to solve are these two equations in the box at the bottom there. We need the x partial derivative of f to equal m. And again, we're going to know what m is. And we also need the y partial derivative of the function to equal n. All right, the main idea is we're going to undo the partial derivatives by integrating, which is the main theme for our course. We're almost always going to undo derivatives by integrating. All right, so make sure you have in your notes both these, the criteria for exactness, and then how we solve the ODE. by solving these two simultaneous equations. Our goal is to solve those for f of x comma y. When you're ready, finally, I know there's a lot of background material that goes into this. Let's get to our first example. All right, and I realize, again, this topic, exact equations, is very dense. So let's go through this together. But of course, you're welcome to pause to make an attempt. But let's just proceed. All right, so we, about a minute ago, addressed that this ODE is exact by calculating these partial derivatives of m and n. All right, you always want to check this. If the ODE is exact, then you can jump down to solving those two equations. If it's not exact, we have to do something else. Fortunately, it is exact. So we can solve these two equations. The x partial derivative of f should equal 2x plus y squared. And the y partial derivative of f should equal 2xy. And then in red, those are the general equations. The x partial derivative of f should equal m, and the y partial derivative of f should equal n. All right, now there's several ways you can solve these two equations. What I would prefer you not do is integrate both of them. Why? Well, integrating is complicated. And if you can get away with just integrating once, if you can be lazy, do it. So we're going to be lazy. Now, you might have implemented this technique that we're about to use in your Calc 3 course. This would have been at the very end when you were introduced to vector fields, specifically two-dimensional vector fields, and asked to determine if the vector field is conservative. And again, if you think back to your Calc 3 course, that means that the vector field is the gradient of some scalar function. We call that scalar function the potential function, borrowing language from physics with perhaps electric potential and its relationship to an electric field. All right, and there was a similar criteria for the vector field being conservative. Instead of calling the components m and n like we are, you called your component functions p and q, just standard Calc 3 notation. All right, and there was this criteria for p and q's partial derivatives for the vector field to be conservative. So this might look familiar, and you might recall how you found the potential function back when dealing with vector fields, conservative vector fields, in your multivariable calculus course. All right, now, regardless of how you solve that in your multivariable calculus course, I'm going to advocate what I consider to be simpler. We're going to pick one of those equations and integrate it. Doesn't matter which one. Generally, you want to pick the simpler one to integrate. And then we're going to compare with the other equation. And this avoids us having to integrate twice, which is correct, you can do that, but I'm going to advocate to be lazy, integrate one of them, compare with the other. All right, so we have a choice. We could integrate the first equation, or we could integrate the second equation. All right, and I'm just going to choose, I think the second equation looks a little bit simpler. We only have a single term, 2xy, rather than two terms like in the first equation. So we're going to integrate the second equation. Since the second equation involves a y partial derivative, we're going to integrate that, cancel that y partial derivative by integrating with respect to y. What we need to be careful of is which variable is the constant. If we're dealing with a y partial derivative, that means x is thought of as being a constant. All right, so I want you to keep that in mind. Now we're going to integrate both sides. Integrating the left side should cancel the partial derivative, giving you the function f. And when we integrate the right side, integrating 2xy with respect to y, we integrate as we would expect with respect to the variable y. So 2xy, that's going to integrate to xy squared, thinking of x as being a constant. But recall, when you integrate, you get a plus c, an arbitrary constant. Now it's a little bit different. Since we're dealing with multivariable functions, this constant that we get, it can actually be a function, but only of the variable that we consider right now as constant, which is x. So our integration constant actually could be a function of x right now. So we'll denote that by c of x to denote a function of x. All right, now we basically have solved for the function f, but we still have an unknown, that constant function of x, which came up due to integrating. So once we determine that function c of x, we've found our potential function, and we basically have solved our ODE. Now, this is the end result of integrating equation 2. We haven't done anything with equation 1. Now, what does equation 1 involve? It involves an x partial derivative of f. So let's take the f of x comma y that we just calculated right there on the screen, and let's differentiate that with respect to x. This is the second step, the comparing with the other equation. We integrated the second equation. We're going to compare that result with the first equation, an x partial derivative. All right, so let's calculate the x partial derivative. Xy squared will differentiate with respect to x to y squared. And since c is a function of x, we can write its derivative as c prime of x. Now, in order for our equations to be satisfied, that x partial derivative has to equal what we have from equation 1. That x partial derivative has to equal 2x plus y squared. And what we're left with is an equation that we can solve for c prime, and then we undo the derivative on c by integrating yet again. All right, so let's write down the equation that we have here. On the left side, we have y squared plus c prime of x. The right-hand side, we have 2x plus y squared. All right, and notice the y squareds cancel out, and that shouldn't be surprising because c is a function only of x. So its derivative, c prime, can only contain x's. All of the y terms must cancel and subtract out, which fortunately they do here. So what we're left with is this simple equation, c prime of x equals 2x. How do we undo a derivative? We integrate. So integrate that one last more time, and you should find c of x equals x squared. We are basically done. There's a lot of work and conceptual ideas that go into this, but notice the work doesn't look too dense on the screen here. Most of the work and ideas are just keeping track of the partial derivatives and integrating what's the variable and which is the constant. All right, so to complete this question, we've now determined what C of X is, and we can plug that back in above to where it occurs in f of x comma y. So we'll just replace C of X with x squared. Since we were integrating in those steps from C prime to C, we might have included an integration constant, a true numerical constant, but we don't need to include multiple constants. The solution to the ODE is the function of x and y equals a constant itself. So what we have right now in the lower left is f of x comma y equals xy squared plus x squared. That by itself is not the solution to the ODE. Notice at the top of the screen, the statement of the problem, in differential form, the right-hand side is 0. What differentiates to 0? A constant. So the solution to our ODE is the function of x and y, xy squared plus x squared, equals a true numerical constant, c. And that completes example 2. All right, if needed, pause to fully understand everything involved here. Reach out to me to make sure you understand the criteria for exactness, how we solve those equations, maybe perhaps where they come from, and then how you actually integrate, keeping one variable as a constant. All right, when you're ready, let's move on to a final example 3. All right, so I want to give you all an attempt at example 3. I know how much you all love trig functions, so I decided to throw some trig functions into example 3 here. So enjoy, pause, and give yourself several minutes to solve this. Go back and review your notes if needed. First, verify the criteria for exactness, see if it is exact, and then solve your 2 equations. We'll check in several minutes. Welcome back. Hopefully you made a good attempt at this. Let's go through it to find out. First, we're going to identify what m and n are. That's just from the given form, differential form of the ODE. And we calculate for m the partial derivative with respect to y. And for n, we calculate the partial derivative with respect to x. All right, and notice those partial derivatives are equal. That means this ODE is exact. That basically means we can solve this by solving those 2 equations. All right, and again, what we're looking for is the function f of x comma y that comes out to give these 2 partial derivatives. Now, example 2, we started by integrating the second equation. Just to get some variety, let's solve example 3 by integrating the first equation. All right, so if we start with equation 1, which is an x partial derivative, to undo an x partial derivative, we would integrate with respect to x. Keep in mind, when you're calculating an x partial derivative, y is thought of as being a constant. So this step of partial integration with respect to x, y is also thought of as being a constant. All right, if we carry that out, integrating with respect to x, thinking of y as a constant, the antiderivative for cosine of x should be sine of x, and the antiderivative of 2x should be x squared. The y terms are thought of as being constant multiples. All right, now the end result is a little bit different here. Because we integrated, we get a plus c, but the constant could actually be a function of the constant variable, which was y. So by starting with equation 1 and integrating with respect to x, we get a constant function, perhaps of y. All right, so that is the end result of solving equation 1. We've integrated the first equation. We're going to compare with equation 2, the other one. And that involves a partial derivative with respect to y. So if we take our function f and differentiate with respect to y, we can then set that equal to equation 2. All right, and if you do that correctly, what you should have are terms only involving y, since c prime of y denotes only a function of y. All right, notice the sine of x term cancels out, x squared e to the y cancels out, and we're left with this equation, c prime of y equals -1. Undo the derivative yet again, and you should find that c of y equals -y. All right, we can plug that back in to the function of x and y and replace c of y with -y. The solution to our ODE would be that function of x and y, but equals a constant. All right, hopefully example 3 went well for you. Again, make sure you follow up with me immediately if you have questions on anything from this lecture. It's very dense and tends to be complicated for students. What I want to do is transition us to basically the next lecture. So let's just consider an example, looks similar to what we've been dealing with. Another ODE in differential form. What could go wrong? Well, let's identify the functions m and n, and let's check if it is exact. And unfortunately, a lot goes wrong. The partial derivatives are not equal, which means this ODE is not exact. How do we solve a non-exact ODE? Well, as it turns out, these are solvable, but they require something called an integrating factor. That's the content of the next lecture.